Hello, my name is Matthew Harrison and I am the Senior Mechanical Design Engineer responsible for Renishaw's REXM High Accuracy Encoder products. I'm going to speak a little bit about REXM encoders and how you go about achieving the best accuracy from them. REXM is a flange-mounted encoder. It's designed to be placed on a flat surface and gently knocked concentric to the rotating axis and then bolted down. The bolts on an REXM ring provide the clamping force which prevents the ring from moving once it's been centred. Larger rings have more bolt holes which increases the clamping force and also ensures that the distance between clamping points is not too great. There's a step on the rear face of the encoder. This is to ensure that the surface area that has been made flat on the mounting face isn't too large. The recommended mounting surface is 10 micron flatness for the ultimate accuracy. We use a tighter spec during the graduation process using highly ground surfaces. The ring itself does not need to be this flat. Early rings were ground to 10 micron flatness. It's found that this was not necessary, as the ring will be consistently pulled to the shape of the mounting surface by the M5 mounting bolts, which exert around 7,000 newtons clamping force per bolt. If the surface is not flat, then the ring will distort to that surface, and the shape of the surface may start to transfer ever so slightly to the scale face. If the mounting surface is flat but swashed and reed heads are axially misaligned, then ring error will result. For a 10 micron flat surface, as recommended, error could be up to half an arc second on an REXM 100 with a 1mm reed head misalignment, which is something that should be easily preventable. Great care has been taken to ensure that the ring profile can withstand the forces involved in centering the ring, provided that the bolts themselves are clear of the ring face when the ring is being centered. REXM rings are easier to center using the taper system. If each bolt is adjusted to the nearest 3 microns, then the ring itself will be centered to on average 1.5 microns. Even if the ring is perfect, it would be difficult to centre an REXM ring to better than 1 micron, as the ring itself will shift ever so slightly when the bolts are tightened down. On an REXM 150, this will contribute at least 3 arc seconds of error. Using REXM with 2 reed heads minimises the need for this excessive centering and ensures that higher order harmonics are minimised. 2 reed heads remove the effects of bearing wander. The system reads the angle of the encoder itself regardless of its centre. In tests, the customer achieved better than an arc second accuracy with 50 microns deliberate eccentricity. Because the encoder is mounted directly onto the axis in question, there is no mechanical hysteresis between the encoder and its mounting surface. The quadrature will reverse down to the electronic noise level of the reed head, which could be as low as 0.5 nanometers RMS.
Hello, I'm Colin Howley. I'm a Principal Electronics Engineer, and I'm going to talk to you about velocity control. The main error mechanism causing velocity error is subdivisional error, or SDE. At most speeds, you don't see the raw SDE, but an alias effect, as the controller samples the encoder signals, because the sample rate is lower than the frequency of the SDE. Normally, the SDE will be the largest error component. At low speed, the frequency of the velocity error will match the SDE, as there will be a number of velocity loop samples within each encoder cycle. At low speed, noise, also known as jitter, becomes important. At very low speed, noise will become the dominant error mechanism. Quantization effect should also be considered. You need fine resolution for a smooth velocity loop. We use dynamic signal conditioning to minimize SDE. To ensure low noise, the optical scheme of tonic has been optimized to produce an excellent signal-to-noise ratio. The finest resolution version of tonic has jitter levels of 0.5 nanometers RMS. Starting with the incremental encoders, signum and tonic have the same SDE levels because the dynamic signal conditioning works in a similar way. The main difference is that the noise level of tonic is lower than the noise level of signum. Tonic has a newer, more advanced optical scheme that has been optimized for that parameter. You will therefore see an improvement when using tonic at very low speeds. Resolute is an absolute encoder. By design, the noise level is not going to be quite as good as tonic because less signal is available due to the arrangement missing out some lines to achieve an absolute code. However, bear in mind that Resolute is capable of a maximum speed of 100 meters per second, but the noise level is still twice as good as that of the leading competitor. It's still an impressive system. Resolute's SDE is only slightly higher than tonic at plus or minus 40 nanometers compared to plus or minus 30 nanometers.
Reed head mounting is absolutely critical and sometimes overlooked. Reed head mount distances must be kept as short as possible and preferably radial in direction so that thermal expansion is not tangential and therefore does not contribute to ring error. The ring itself should not change shape with temperature because it should expand uniformly, particularly if it's mounted onto a stainless steel surface. Signum reed heads work up to 12.5 meters per second. Tonic reed heads up to 10 meters per second. The encoder itself can rotate much faster than this, up to 35 meters per second for an REXM 100. Above this speed, the ring may start to change shape slightly, although the overall error should stay within spec until 6 times this speed. After this point, deformation may start to become plastic and therefore irreversible. An REXM 100 will withstand 1000 G without slipping. The reed head will withstand 100 G non-operating and 50 G during operation. This is all pretty robust for a sub-arc second encoder system. REXM rings are suitable for error mapping. This is because they are very stable, so once the error is determined, it does not change, even with careful reinstallation. As an example, 2 REXM 300 rings are calibrated against each other. One ring is then turned 33 degrees relative to the other, and the calibration repeated. Each time the top encoder's error moves with the top encoder, and the base encoder error stays fixed. Averaging the results together provides the base encoder error, and realigning the plots provides the top encoder error, plus or minus 0.4 arc seconds. Mapping this and subtracting it from the 11 previous results gives the error mapped encoder accuracy, or 0.1 arc seconds in this case. All this was achieved using standard off-the-shelf signum reed heads and REXM encoders. Not bad for such a robust system that can work in many harsh environments. Using extra reed heads will bring the overall error down. 2 heads cannot compensate even ordered errors, for example ovality, 4 per rev and so on. 3 heads compensate all but the third order errors, for example trilobularity. More heads remove more of the lower order harmonics, leaving just the higher order errors, which tend to naturally reduce in amplitude. Well, that sums up our advice on achieving the best performance from Renishaw's high accuracy REXM encoders. I hope you found this useful, and thank you very much for listening.